All right, next I wanted to look at one final type of motion that the planets can exhibit relative to the zodiac constellations. We've already talked about the apparent east to west motion of the planets, and this is called proper motion. However, occasionally the planet's motion can reverse itself and go east to west. And so this rather confusing type of motion is called retrograde motion. So let's just review for a moment what causes the proper motion. You have the Earth going around the Sun, and in the process of the Earth going around the Sun, Jupiter is also going around the Sun, but more slowly. Okay? And the reason why it's going more slowly is that there's less gravity force acting, and that lower gravity force means that it doesn't have to move as quickly in order to complete an orbit. And it's also got farther to go. So in the amount of time that it takes the Earth to go all the way around, Jupiter has just gone through one zodiac constellation. And so it's going around the Sun, and from our point of view, looking down on the Earth's North Pole, this is the westerly direction. This is the easterly direction. So that's our proper motion. Okay, so in the time of the Greeks, they believed that the Earth was at the center, and that it was actually Jupiter that was in orbit around the Earth. And so either way, you would get this west to east motion with the correct explanation or with the explanation of the Earth being at the center. But what makes all of this even weirder is that occasionally Jupiter can reverse its path, and it doesn't do so for very long. But when it reverses its path, this is called retrograde motion. And so in trying to understand why the planets move the way they do, this had to be explained. And so this was a very difficult sticking point in the history of astronomy, which we'll be getting to in a little while. But let me just show you a picture of what's really happening with retrograde motion. And it's a little easier to see with a planet like Mars. So in this picture, what we see is that there's the ecliptic plane in the dotted line, and the red path is the path of Mars moving, and so Mars then moves most of the time from west to east. But then occasionally, in the center there, you see that from July 1st, there's August 1st, but then it starts moving backward from September to October, and then starts moving forward again a little later on. And notice that you have the background of zodiac constellations that it's moving through. There's Capricorn, there's Aquarius, and it's on its way to Pisces. Okay, now to try to understand this better, we can look at a view of the Earth and Mars from a top view, in which this would be point 1 at time 1, and there would be Mars. So this would be the position of Mars at the same time that the Earth has its position labeled by the same numbers. Now it turns out that the Earth is moving around the Sun faster than Mars is, for the same reason that Jupiter is moving more slowly than the Earth. Mars is farther out. It's also moving more slowly. So the Earth can overtake and pass Mars. So you see, that's what's happening here. There's Mars moving a little more slowly. Here's the Earth catching up, and then the Earth gets ahead of Mars here. And so the 7 and the 8 here are ahead of Mars in terms of where Mars would be, because Mars is moving more slowly. But what that does to our viewpoint on Mars is it appears to, as the Earth overtakes and passes Mars, it appears to cause Mars to move in the backward direction. Okay, and so this is simply because we're looking at it from a different angle. And that angle is measured with respect to the fixed background of stars that are behind it. Okay, and so this gives the illusion that Mars isn't really moving backward. It's only because the Earth is overtaking and passing Mars and then looking at it from a different angle, and we're projecting that onto the fixed background of stars. That's what's giving this illusion of Mars moving backward in the nighttime sky. But associated with this retrograde motion, we have this apparent east to west motion. And so the cause then, just to summarize what I was saying, is that the Earth overtakes and passes Mars. So here's the Earth moving along like this, faster than Mars. I'll exaggerate it a little bit here. Here's Mars moving more slowly, while the Earth is moving faster. Not really this much of a difference, but this could be like 0.1, 2, 3. This would be 1, 2. That's where Mars is at those same times. So we see then 1 is going to be here. But then when we get to 2, it's looking like it's going backwards for a while until it gets to here. And then by the time it gets to here, then it starts moving forward again. Okay, so this only happens then when the Earth is at its closest point to Mars. And at this point, then, it overtakes and passes Mars. And that gives the illusion of backward motion. Now, in the time of the Greeks, they were interested in this from an astrological point of view. It was considered a very unlucky time, for example, when Mars was in retrograde. And you would never have, say, a wedding, or it might be a blood wedding if that were to occur. Or you wouldn't start a war at that time because everything would be working against you. All of the gods would be would be demonstrated by this astrological alignment to be in an unfavorable situation for a coronation. No, forget it. Wait till Mars gets out of retrograde. And so they were very, very interested at the time in predicting when these planets would, if they were in their proper motion, when they would get out of this very unfavorable configuration and then get back to their more favorable motion again. And so this is important then from the standpoint of the history of astronomy. You go, well, who cares? You know, if it just backs off for a short period of time and then moves on ahead again, seems like it's not that big of a deal. But in terms of it being a weird kind of motion, it actually played a key role in helping us to understand the true nature of our place in the universe. So, with that introduction, I'd like to move ahead to chapter 3, which is the history of astronomy. And we say, well, why are we interested in the history of astronomy? And I think maybe one of the answers to that is simply that we don't want to make the same mistakes that were made in the past. And so why reinvent the wheel if all of these different attempts at understanding the universe that have been tried, and some have failed, some have succeeded. So if we have a perspective on history, we can perhaps prevent ourselves from making some of the bonehead mistakes that have been made in the past. Okay? And so, for example, the Greeks concluded, and we'll see why in a moment, that the Earth is at the center of the universe. Of course, we say today, well, that's silly. We know that that's not true. But they actually did some very careful experiments and measurements and came to the inescapable conclusion, at least from their own point of view, that it was the Earth that was at the center and everything else was moving around the Earth. And so what can we learn from this? Well, the lesson that we learn from this is don't put the Earth in a privileged position. Or another way of saying that is don't give the Earth an exaggerated sense of importance. We live in a big universe, and it's natural for us to want to think that we're more important than we really are. And so that can bias the way that we look at data. So this is a mistake that the Greeks made to go, well, how could we ever make such a silly mistake today? The answer is, well, we look out at galaxies and we see all the galaxies moving away at ever-increasing speeds from us. Okay? And so you could be tricked then, if you hadn't learned from the lessons of the past, that our galaxy, and that in particular our planet, are at the center of the whole universe. And yet there might be 2 trillion galaxies in the universe, and so why should our galaxy be in a position of exaggerated importance? Okay? And that is an example of things that we can learn that can still be applied to the world that we live in today. And so, keeping in mind that astronomy has very ancient roots, we believe that some of the earliest observations were based on survival. Okay, so we would look at things like the appearance of Orion in the nighttime sky often preceded the Nile floods. And so it was believed at the time that this Orion constellation had mythological powers that would then allow for the Nile to overflow its banks, and then that would fertilize the soil, and that would be the time to plant. Okay, and so that would be an example then of a survival-based observation. Okay, and so as time went on, the Greeks took the work of previous civilizations including the Babylonians and the Egyptians, and there's some evidence that in Africa too they were making some important observations, and they combined these together about 5th century BC, and came up with an argument for whether or not we lived in a geocentric or heliocentric world. Now, geo means Earth, centric is centered, so this is Earth-centered. Or do we live in a heliocentric? Where helio is sun, so that's sun-centered. And so this debate then went on for quite a while. And so there were some arguments in favor of the geocentric model. Not just that we wanted our Earth to be in an exaggerated position of importance, but actual physical arguments in favor of the geocentric model. One, the Greeks asked, if the Earth is actually in motion, then why don't we feel the motion? Certainly, if you were in a carriage and you're being moved along by a horse or something, you would feel the motion. Every time that anyone goes anywhere, you're feeling the motion when you're walking from one place to another. You can tell that you're going from place to place. And so if the Earth is in motion, then why aren't we feeling the fact that the Earth is in motion? If it's moving around in a circle, they saw things like the mud on a wheel. And that mud would go spinning off the wheel. So why don't we go spinning off the Earth? Why aren't we at least feeling the motion, getting a little bit seasick, at least? So that's one question. And I hope as I go through these, I don't talk you into believing in the geocentric model, because this is obviously incorrect. Let me just emphasize that here. So these are the arguments in favor of this incorrect model that we can see after we've spelled this out, that there actually were quite a few arguments in favor of the geocentric model, so that maybe we can forgive them for having made such a horrible mistake. Another question is, if the Earth is in motion, then why, if you jump up in the air, doesn't the Earth leave you behind? So let me try to make this more clear. The Earth is moving at about 1,000 miles an hour. Due to the Earth's rotation, each day it's moving 20, at the equator at least, the circumference of the Earth is 25,000 miles, so that's 25,000 miles in 24 hours, or about 1,000 miles an hour. That's pretty fast motion. And so if the Earth is moving that fast, 1,000 miles per hour, and then you jump up in the air, then why doesn't the Earth go flying out from under you, and you go flying out that door and end up rolling around in the parking lot 3 blocks away? Okay? That just isn't observed to happen. And so we wouldn't have to worry about not feeling motion sickness, and we wouldn't have to worry about the Earth leaving us behind. We just go, well, hey, wait a minute. What if the Earth isn't moving? Then isn't everything okay? it solves all of those troublesome questions. Another question that the Greeks had is, why doesn't the Earth, if it's rotating, leave the atmosphere behind? Okay, so here the atmosphere isn't even in contact with the Earth. So you've got these molecules in the atmosphere, and then here's the Earth moving out from under those particles at 1,000 miles an hour. Then shouldn't that produce gale force winds on the order of 1,000 miles an hour all the time? Now, in the center of the eye of the most radical E6 tornado, you might get velocities of 300, 350 miles an hour. Never 1,000 though. And in general, our velocities are way, way lower than this, hardly any wind at all. And so the Earth doesn't appear to be leaving the atmosphere behind at all. If it did, all the leaves on the plants would be torn off. There'd be no oxygen being produced by plant life above the surface of the Earth, and we'd all asphyxiate because we wouldn't have any oxygen. Okay, so that's just not happening. And so that's another question that the Greeks have that they couldn't answer. Now these can all be answered, by the way, very easily with the correct laws of physics, but the Greeks didn't have the right laws of physics. And so that's one of the reasons, the main reason, I should say, why they weren't able to answer these questions. Another question that the Greeks had was, and of course they tended to favor the geocentric model because they couldn't answer these questions. Another one that they had was why no stellar parallax? So the Greeks weren't dumb. They realized that because of the motion of the Earth around the Sun, we should get some apparent motion of stars and their constellations. So if we just look over here for a second, let's say that this is the Earth going around the Sun. And here's a more nearby star. And then here's some more distant stars, not necessarily all at the same distance away. Then, when the Earth looks at this more nearby star, at a certain time of the year, it would seem to be here. But then 6 months later, that star would be up here. So that star would move across the fixed background of stars over a 6-month time period. Okay, so this then would be the motion that we call stellar parallax. Okay, so let's just define that more clearly here as being the apparent motion of stars due to the change in position of the Earth as it goes around the Sun. Now, apparent here means it's not real. So, in other words, if you had a constellation like the Big Dipper, okay, and you have something like this, you wouldn't know which star would be a more nearby star. You couldn't tell. So you'd have to look at all of them and see if the pattern of the constellation itself changed because one of the stars was moving relative to the other one. So it might be this star. So this star might move like that over 6 months, and then like that over the next 6 months, then back and forth, and just have an average position of being there. And so that's the kind of thing that you could observe then if you looked at all of the stars and did a comprehensive search of the sky. You could show that if the Earth were in fact shifting its position on a more nearby star relative to the more distant stars, that you would get a shift in the position of certain more nearby stars over a year time period. And so the Greeks searched for years for this. And so they were looking there for a change in the position of any star in any constellation, not knowing which one to look for. And they found nothing. So things are starting to add up then against the heliocentric model. Because if the Earth is in motion, we can't explain why you don't feel the motion. We don't know why the Earth doesn't leave you behind when you jump, or if you could bounce a ball. Imagine the Earth sliding out from under that ball would go flying in the direction opposite the Earth's rotation. Why don't we have gale force winds all the time? And there's no stellar parallax. So the evidence is looking pretty bad for the heliocentric model. And that's why these are arguments in favor of the geocentric model, is that they either couldn't be explained in terms of the Earth moving, or the data that was collected was non-existent. And so let me try to explain to you why these are faulty reasoning by the Greeks. First of all, for the first one, why don't we feel the motion when the Earth is rotating as it orbits the sun? And the answer is the motion is too gradual. Or put in terms of physics, we could say the accelerations are low. So an acceleration is a change in velocity. You can be moving pretty fast. But if there's no change in velocity, then you only feel a change in velocity. And that's what an acceleration is a change in velocity. So you'd be going 1,000 miles an hour, but if there's no sound and there's no bumping, there's no acceleration, then you're not going to know the difference. It's just normally, if we're going that fast, we'll hear an engine, hear the vibration, there'll be little rumbling sounds, and that's our clue that we're going really fast. But let's say it's in a circle. Let's say that this is a kid's amusement ride, like a merry-go-round or something. Instead of it going this fast, let's say it's just going 1 rotation a day. Okay, and the child is sitting here. Is the child having any fun if it's going 1 rotation a day? No fun at all. He said, I can't feel a thing. You know? Stop wasting my time. Get me off of this thing. Such a nice kid. And so the motion's too gradual. Okay, and So that's the reason why we don't feel the motion of the Earth. A really sensitive measuring device might be able to feel that, but our human senses aren't sensitive enough to feel something that has an acceleration that's that low, even though the velocity is high. Second question, why doesn't the Earth leave you behind when you jump? Well, the answer here is that you share the Earth's motion when you jump. What does that mean? Share the Earth's motion. Well, let's look at another example. Let's look at a bus that's moving at 35 miles an hour. And then let's say you're in the bus and you decide to jump. Be at the middle of the bus like that. You jump up in the air. Let's make sure you don't hit your head. Put it a little higher here. So as you jump, the bus is moving. So the actual path that you take until you land back on the bus is going to look something like this. And this is the exact same kind of path that a projectile follows if you throw it on the surface of the Earth. Okay? And so what we see here then is that when you jump up in a bus, if the bus is moving at 35 miles an hour, the bus is moving just as fast as you are in the horizontal direction. The bus doesn't leave you behind. You already know that. You know that if you jump up in a bus, you're not going to go slamming into the back of the bus, right? Unless the bus driver is mischievous and decides to hit the accelerator at the moment that you jump up in the air, then it could accelerate out from under you. But that's not happening here if the bus keeps moving at 35 miles an hour. So what we see here is the same thing that happens on the Earth. You share the bus's motion in the same way that you share the Earth's motion. So if you jump up in the air, it looks like you haven't gone anywhere because the Earth has moved just as far as you have in that same amount of time. So here's where you were. Here's where you are. It's the same spot. You're moving this far, but the point that is under you is moving just as far in the horizontal direction as you are. And so that's why the Earth doesn't leave you behind when you jump. Now there's a presumption that the second you lose contact with the Earth, that you start slowing down. That's a presumption that's wrong. That is not true. The reason why we believe that that's true is on the surface of the Earth there's friction. So if I take something like this chair and I move it, it comes to rest the second I let go of it. Okay? But that's not true in free space. That's only true because of friction being a force on the Earth. Okay? And so that's basically a mistake that the Greeks made because they didn't understand the correct laws of physics. In problem 3, why doesn't the rotating Earth leave the atmosphere behind? Same reason. Atmosphere shares the Earth's motion as well. Why? Because anything that was on the surface of the Earth at one time became the atmosphere. This could be plants giving off atmosphere, or it could be volcanic eruptions. Whatever the source of the Earth's atmosphere was at one point moving with the Earth, and so it's still sharing the Earth's motion. And so it's moving right along with the Earth, and so it's not just going to come to a screeching halt the second it loses contact with the Earth. That's the wrong laws of physics. It's going to keep moving in a straight line at constant speed. That's called Newton's first law of motion, the law of inertia. Okay, so that's another way of saying this then, is that objects have inertia, which is a resistance to changes in speed. Okay. Question 4, why no stellar parallax? Well, even the Greeks realized that this was a possibility. The answer to this is that the distances are too far to measure the angles. just that little tiny bit of motion of the Earth around the sun seems like a lot of motion to us. But in relationship to the distances to the star, the angle that you would have to resolve here to be able to see this angle here, would end up being around 1/100,000th of a degree. Okay, and so this thing is really stretched out. So this angle is almost zero. If the angle is almost zero, that means that the motion is not detectable. And so if you get far enough away from something, now I look at this pin really close up, looks really big. But if I put it far away, it looks pretty small, okay, because its angular size has changed. Here, the angles that you would have to measure are so small that it would be like measuring the angle from one end of a dime to another at a mile's distance away. And I can't even see a dime at a mile's distance away. But you'd have not only be able to see it, but be able to measure the angle between one side of it and the other. Now, we can do this now. And so in the last 100 years or so, we've been able to make these kind of measurements and have seen the parallax of the stars. But in the time of the Greeks, they were nowhere near being able to use that kind of precision angular measuring devices. And what finally tipped the scales, though, for the geocentric model for the Greeks was number 5. Why is there retrograde motion? Even though retrograde motion doesn't seem like that big of a deal, it is strange enough so that it should be able to identify an incorrect model from a correct one. And so that's often what scientists look for when trying to decide between one model and another, is some piece of data that is so strange that there's only one way of explaining it correctly. Okay? And so that's what they sought to do with this idea of retrograde motion. And so this guy named Ptolemy figured out a way to predict retrograde motion. But he solved it. The problem was he solved the problem with an Earth-centered model. So in other words, he assumed the Earth was at the center, and he was able to predict retrograde motion just fine with his model. And so let me just show you, by looking up at the data projector, how, well, here's another look at retrograde motion here. We can see how this is Mars, Mars moves a little faster than some of the more distant planets, so it's easier to follow the retrograde motion. But that retrograde motion was quite observable. And so here in Ptolemy's model, the Earth is at the center, and the planets orbit around the Earth in what's called an epicyclic motion. Okay, so it's the planet, you can imagine this like almost being like a bike tire that's rolling around on a circular track. And then the planet you can imagine to be one point that's painted onto not quite the rim of this thing. It would have to be inside a little bit from the rim. But if you've ever looked at a reflector from a tire that's moving, the reflector does this kind of motion if the reflector isn't right out at the edge. So this then we could call, or we could have it going in the other direction. Probably be better. We have it going this way. Then this would be the proper motion, which would be west to east. And then here we'd have the retrograde motion, which is east to west. And what Ptolemy found was by adjusting the size of the smaller circle and the size of the bigger circle, he was able to predict when different planets would go into retrograde motion. So this was in the 1st century AD. And this, of course, is incorrect. This is called the epicyclic model. So we'll actually get to some correct models pretty soon. So you're not just learning things that aren't right. But these are some mistakes that were made. And we can learn from these mistakes. That's why we're going through this. Another thing we can learn is that you can get the right answer from the wrong physical model. Look at this. And so everybody just bought into this idea, well, okay, I give up. The data is showing that Jupiter is going into retrograde motion in 2 years from now, from September 15th to October 3rd or whatever. And that's exactly what Ptolemy's model is showing. And so you must be right. And it must be geocentric is correct. And so the geocentric wins then for something like 1,600 years. Now, this is not to say that there weren't some very strong heliocentric supporters. There were some Greeks that had figured out the distance to the sun, and even though their distances were wrong, they concluded that the sun must be much bigger than the Earth. And so they then proposed the question, why on Earth, or why in the universe, would a bigger object be circling around a smaller one? Doesn't it make more sense to have the Earth going around the bigger object? And the Greeks had determined that the sun should be much bigger than the Earth. And so that was a strong argument. But all of these other arguments here that couldn't be answered at the time were sufficient for everyone to buy into this idea of the geocentric model. Now, this is not to say that there weren't probably some scientists that didn't buy this and wanted to go against it. But the strength of the belief was taken up by the church, and the church became very powerful. And so around that same time, if you were trying to argue for the Earth being at a less privileged position in the universe, you might be executed. And so this is perhaps another very good reason why nobody challenged the geocentric model for 1,600 years.